Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to introduce the inner product. So in this topic, we will define and describe how to calculate the inner product. We will note how it seems to suggest the angle between the vectors, and then we will make some additional observations. So, given two vectors u and v, where the first entry is u1 and u2 and v1 and v2 respectively, we will define the inner product between these two vectors as u dot v, or angled brackets containing the vectors u and v, and this is the first entry of u times the first entry of v plus the second entry of u times the second entry of v. That is the sum of the pairwise products of the entries of the vectors. In secondary school, you may have called this the dot product. In engineering, you will usually refer to it as the inner product. The bracket notation is used in quantum mechanics, and because of that, we're going to start using that notation now so that you become familiar with it. Now, something that's very important to remember is that the inner product is not multiplication. You understand the multiplication of real numbers, but when you multiply two real numbers, you get a real number back. So we're going to notice that the inner product shares some properties of multiplication, but definitely not all. The inner product of two vectors is a real number. It is not a vector. The angled bracket notation actually is nice because it emphasizes that the inner product is something different from a vector. This is a real number. I am a number, not a vector. Copyright ITC. This is not a vector. Do you understand? Excellent. Copyright BBC. Now, for example, here are two vectors, u and v. If we calculate the inner product between these two, we get the value 1.65. So it's 1.5 times 0.7, negative 1.2 times negative 0.5. Now here are two other vectors. U is again the same, 1.5, negative 1.2. V is negative 0.4, 1.6. Taking the inner product, we multiply the first two entries and add to that the product of the second two entries. This now gives us a value of negative 2.52. As a third example, these vectors are at right angles, and you'll remember if u is the vector 1.5, negative 1.2, if we flip the two entries and negate one of the entries, as we do here, we get a vector that is at right angles to the first. If we calculate the inner product here, we see that the inner product is 0. Finally, if u and v are the same number, notice that it is just the sum of the squares of the entries of the two vectors. That should look familiar. We're going to discuss that later. In this case, it's 3.69. Now, based on these examples, we may note some properties. If the angle between the vectors is acute, then the inner product seems to be positive. If the angle is right, or the vectors are orthogonal, the inner product seems to be 0. If the angle is obtuse, the inner product is going to be negative, or at least so it seems. We're going to take a look at that in a subsequent talk. However, let's make some observations about the inner product. Here are two vectors, u1, u2, v1, v2. Note that the inner product of u and v is equal to that sum of products. But multiplication of real numbers is commutative, so I can change the order, and you'll notice that that is just the inner product of v and u. We say that the inner product is symmetric. So u dot v is equal to v dot u if you use the high school notation. Now, let's consider these two vectors again. Remember that the scalar multiple of a vector is that scalar multiplied by each of the entries of the vector. So a real number a times v is just a times the first entry of v and a times the second entry of v, and thus the inner product of u and a times v is just the product on the right hand side. But notice we can factor out a common factor of a. And notice that what's in the brackets is just the inner product of u and v. What this says is the inner product with a scalar multiple of that vector is the scalar multiple of the inner products. And using the dot notation, here we see what it looks like. Now, consider the three vectors u, v, and w. Recall that the sum of v and w is just the sum of the first entries of v and w and the sum of the second entries of v and w. Thus, the inner product of u and the sum of v and w is the expression on the right-hand side. But by the properties of the real numbers, I can just expand that and collect to see that it is the sum of these two sums of products. But wait a second, isn't the first one just the inner product of u and v, and the second one the inner product of u and w? What this says is that the inner product with a sum is the sum of the inner products. And again, writing this using the notation of the dot, again, it looks very similar. The inner product distributes over vector addition. So in this topic, we've introduced the concept of the inner product. It is the sum of the pairwise products of the entries of the two vectors. It is a real number. The sign seems to say something about the angle. Specifically, if the angle is 90 degrees, it seems that the inner product is 0. We've also made a few observations. It is a symmetric operation, and we've seen how it interacts with vector addition and scalar multiplication. Here are some references, acknowledgements, the colophon, and a disclaimer. Cheers!